Here are a few examples about solving problems using properties of similar polygons. So number 3 there says, the two figures below are similar. Find the missing side length. And so we need to compare apples to apples and oranges to oranges, or we need to compare the small triangle to the large triangle. So if this is the small triangle and this is the large triangle, when we set up our proportions, we need to make sure that these are in line with each other, and we'll show examples of that. So whenever I set up my proportion, I always keep the same thing consistent. It's always going to be two ratios compared by an equal sign. And I'm going to set that up before I do anything else. And then I want to decide what the ratios are that I'm going to be using. So we have the small triangle compared to the large triangle. And we need to compare corresponding size. So if we look over here, the largest is this bottom side here, or 32. That is going to be the biggest side. That's the biggest of the large triangle. And the bottom here is also the biggest. For 8 is the biggest of these sides. So when we set this up, we have to make sure that we don't have any units cross. They have to be either straight up and down or straight across. And what I mean by that is, let's say that we say that all the small triangle information has to be in this proportion right here on the left, and all the large triangle information needs to be right there on the right. Okay, so we'll make sure that we stack it this way. The other thing that we need to pay attention to is stacking it this way, left and right. So if we pick the biggest, in this case we want the biggest right here, so the biggest has to be in the numerator. So the biggest side of the small triangle is 8, so that has to go in the numerator. And the biggest side of the large triangle is 32, so that has to go in the numerator. And what are we going to compare that to? Well, the question mark over here is the smallest side of the triangle. And if we look at this, we have 20, 28, 32. So 20 is the smallest. And so we need to compare that. So both of the units in the denominator are going to be linked to the smallest side. And this one has to come from the small triangle. So the small triangle over here is, we're not sure, so that's going to be x. And the smallest side over here, that is 20, so that goes in the denominator under the large triangle. And now we get to go ahead and solve it. And again, we're going to use our means and extremes. So all we do is we take 32 times x, and we're going to set that equal to 8 times 20. And 8 times 20 is 160. And that is equal to 32x. And divide by 32, and divide by 32, and we get x, because the 32's cancel, and we get x is equal to 5. Or the small side over here is equal to 5. The next one says compare the perimeters of the similar figures. So the perimeters are just adding them together. So the small triangle, the perimeter of the small triangle is equal to 5 plus 7 plus 8, which is equal to 20. And the perimeter of the large triangle is 20 plus 28 plus 32. And so that ends up being 80. And so when we compare that, we can say 20 divided by 80 and so we end up with both those are divisible by 20, so we end up with 1/4. So the ratio of the perimeter of the small triangle to the perimeter of the large triangle is 1/4, and that's the same for each of the sides. Next example we have is 4, and again it says the polygons are similar, solve for x. So we have some other information. The scale factor from A to B is 3/4. So I'm going to do the same thing that I always do. Right now we're setting up a proportion. And whenever we set up a proportion, we always have a divide sign, an equal sign, and a divide sign. And we always have to compare the same things. So we're going to compare polygon B with polygon A. So the scale factor here is given. So I'm going to add the scale factor, and I'm going to say scale factor goes in the denominator. So which is the scale factor of B? So A to B, 3 to 4. B comes second, so 4 comes second. So that's the scale factor of B, and that's the scale factor of A. And that makes sense because A looks a little bit smaller than B. A should be a little bit smaller than B. Now we're going to compare the side lengths, or the sides of it. So the side of B that is given is 12, and the side of A that is given is 2x minus 5. And then we're just going to go ahead and do our means and extremes again. So 3 times 12 and that's going to be equal to 4 times 2x minus 5. And then we can go ahead and distribute on the right side here. 4 times 2x is 8x. 4 times negative 5 is negative 20. 3 times 12 is 36. Then we want to combine our like terms, so we can add 20 to both sides. Then we get 56 is equal to 8x. And then we can divide both sides by 8. And we get 7 is equal to x. We have another example where we have the polygons are similar, solve for x. And so again, we want to compare the same triangles via a proportion. And if we're looking at this triangle on the right, this one is clearly bigger than this one on the left. So then we have the large triangle, and then we have the small triangle. So when we set up our proportion, we want to compare the small triangle. So all the dimensions are going to come from the small triangle there, and we're going to compare that to the large triangle. So as we look over here, we're looking at this triangle, and it looks like the side that has the X in it is the biggest side or the largest side. So we have the biggest, which is going to be 3x plus 10. So we put the biggest in the numerator, so all the biggest have to go in the numerator. So as we look at the triangle on the right, the biggest is going to be 48. And we can compare that to either side, really, whichever one we want. I'm going to pick the smallest. So the smallest over here is 25. And so the all smallest information has to go in the denominator. And the smallest over here, so that is going to be 30. Then we do our means and extremes again. We have 25 times 48. And that is going to be equal to 30 times 3x plus 10. So then we can distribute the 30 into the 3x plus 10, and then we get 90x plus 300. And that is going to be equal to 1200. Guess we'll probably draw a little line right here to separate that. Then we can subtract 300 from both sides of the equation. And we get 90x on the right side because our 300s cancel. And we get 900 on the left side. Then we can divide both sides of the equation by 90. and we get x is equal to 10. We have example 6. It says the ratio of the model car's dimensions to the actual car's dimension is 1 to 56. So the model car is smaller than the actual car. So 1 is the small car, 56 is the large car. The model has a length of 3 inches. What is the length of the actual car? So again, we want to set up our proportion. And I'm going to do the same thing that we always do. So we have the model, which is probably going to be a little bit smaller. And then we have the actual. So all the dimensions are going to come from the actual car here, and all the dimensions are going to come from the model car here. Now the ratio is given as 1 to 56. So I'm going to put the ratio here, 1 to 56. Does 1 go for the model car or does 1 go for the actual car? 1 goes for the model car. And 56 goes for the actual car. Next, the next dimension we're given is the model car has a length of 3 inches. And this one is length. And then it asks, what is the length of the actual car? So when we're trying to find length, we're going to use our variable. And then we can use so we can see that we always have our units are always stacked or straight across. So straight across is the ratio, straight across is the length, up and down is the actual, up and down is the model. So we do our means and extremes, and we can say three times 56 is equal to 1 times x, which is, I can write down 1 times x, and 3 times 56 is 168 inches is equal to x. Now I want to show one more example for this one. So this is one way to do it. Another way that we could do it is we could set up our proportion, and we could use the ratio here and the length here, and we could use the model. Let's say the model goes in the numerator and the actual goes in the denominator. Now this is just another way to do it. So we can see that we kind of switched where our units go. So the ratio we were given is 1 to 56. So 1 is for the model, 56 is for the actual. Then the length that we were given 3 inches is the length of the model. So length and model match up right there. So that's going to be 3 inches. And the actual, we're not sure, so that's going to be x. And then again, we do our means and extremes. So here we have 3 times 56, and that is going to be equal to 1 times x, which is the exact same thing that we had just calculated. So we end up with 168 inches is equal to x. So the point I'm trying to make here is it doesn't matter where you put the units. The only thing that matters is that you don't have part of the ratio in this left fraction and part of the ratio in this right fraction. You want to make sure that you have them either straight across or straight up and down. Two things to think about. Are two polygons congruent if they are similar? And we have a perfect example here. This triangle and this triangle. It's stated that they're similar. So these triangles are similar. Are they congruent? No. So are two polygons congruent if they are similar? So this one is going to be no. Are two polygons similar if they are congruent? Yes, they always will be. They will always be similar. In this case, the scale factor, where in the first example 3, we calculated the scale factor of 1 to 4. And in example 4, we were given the scale factor of 3 to 4. In example 6, we were given the scale factor of 1 to 56. In the case where two polygons are similar, if they are congruent, the scale factor would be 1. So that's how two polygons would be similar if they were congruent. They'd have to have a scale factor of 1.